not, oh, good. Continue. Okay, so I'm gonna talk about contingency tables, and so let me get to that. Let me tell you what they are. So I think probably most of you know contingency tables are just matrices with non-negative integers, which sum in rows to i's and in columns to bj's. So if so TAB is a set of such matrices, and sort of Roman TAB is the number of such matrices. And the main problem is to compute TAB. So since we have a small number of you, is everyone okay with that? Do you all, can you all see and understand what I mean by contingency tables? Yeah, so do this. Okay. Okay, so the main problem is to compute the number of contingency tables, and by that there are lots of different things that could possibly mean. And you can think of a formula, an algorithm, asymptotics, and most recently I started thinking about various bounds on the number of contingency tables. And in reality, what you want to do is you do your best. You cannot do everything. So I'll continue, and I'll start with some numerical examples because they're rather entertaining in some, I mean, if you like those kind of things. So the first example is if you have 3 by 3 matrices and the sums in each row and each column is equal to 1, then the total number is 6. That's something that you can all see, I'm sure. Yeah. But it might be a little harder to figure out if this is 3 by 3 matrices with the total sum equal to 100, then it's actually the number of such matrices is about whatever it is, 13 million. And if you have 10 by 10 matrices, sum is equal to 280, then it's actually quite hard to compute. This is already 10 to the 59, and if you have so that's from a Canfield-Mackay paper. If you have 30 by 30 matrices and sums and rows and columns are equal to 3, that's an even larger number. But all those numbers can be computed exactly. So this is one of those things that this number is really an exercise. This is not too difficult to obtain, but that number is very difficult. So these are 9 by 9 numbers with a fairly large row and column sums, and you can see that this is 10 to 279, and there is no way to do it by a simple computation. Okay. I don't see, I'm sorry, I see there's a question, but if you're not going to say it, I'm not going to be able to read it.
Very well, sorry. I was trying to count through the contingency tables for the first case, and I swear I can think of 7 of them, one for each sort of inverted, what am I trying to think of, permutation matrix, and then one with all 1/3.
Yeah, so they have to be integer. Sorry, man.
Oh, sorry. Okay. I completely blew by that. Thank you.
Of course, it's important. Otherwise, you'll have a lot of matrices. So those are the things we know. So those are, so here are a few more numbers. If you're watching it like I'm watching it on a big screen TV, you probably cannot see any numbers, and it's mildly intentional because you're not supposed to. This is just to show off that there are some people who do calculations. Some of these calculations have history. So if you look at so the first one by Desjardins is actually, so Percy Diaconis, when he was writing a paper, he asked him to do this calculation. The reason he did it, he had an access to to a giant Cray computer, multiprocessor computer, which just did it by force. And of course, with a much smarter algorithm, Jesus Diluera figured it out in a matter of seconds for both this number and some bigger numbers like this one. Okay, that probably took a few minutes. So those numbers we know exactly. So here is something that we don't. And it's actually, so if you have already 15 by 15 matrix, then if the sums are large, you can figure out sort of the leading term. You can figure out this up to roughly maybe 15, 20%, but that's as good as we know this number. If you have 100 by 100 matrices, then it's even harder. These are just uniform matrices. So the exponent here is some large number, 10 to 33,000. And so we don't know the answer in these cases. This is just guesses. And if you have non-uniform marginals and you have fairly large matrices, you're not going to be able to compute anything at all. So I looked into that, and there is no way to do it in our lifetime. That's it. So that's about it for specific numerical examples. Can I move on?
Why do people care about the specific examples?
Yeah, they do. I'll tell you much more in a minute. I mean, so let me do a little bit more examples. The first one is basically the same example as on the very first page, just for n by n matrices. That's our permutation matrices in this case. The second example is when you have row sums and column sums all equal to 2. In that case, like in whenever you have a fixed row and column sums, the number of such tables is always pericursive. And by pericursive, I mean there is a polynomial recursion of this kind. You can see C of n is equal to n squared times C of n minus 1 and so forth. And that allows you to get asymptotics. And also, can everyone see? Yeah. However, when k is equal to 3, the linear recursion is written here in such a way that you cannot read it, and it's also intentional. The asymptotic is still fine, but the numbers themselves are just horrible. This is a complicated sequence. The linear recursion allows you, the polynomial recursion allows you to compute it efficiently, but that's all it does really. It doesn't really explain what's going on, and it comes, the whole point is that you can construct this linear recursion from a certain order in differential equations and vice versa. So this really means that the generating function is a solution of a nice differential equation. So, so that's it for examples. I'm gonna, before I explain the various connections and applications, let me tell you some news. Those are all bad news. And the bad news is counting the number of contingency tables is actually hard. It's computationally hard. It's a Sharpie complete that was shown by Narayanan, and just a few weeks ago we showed that the number of contingency tables strongly Sharpie complete. And by that we mean when AIs and BJs are given in unary. So to put it in plain language, it should take exponential time even when row sums and column sums are polynomial, not exponential as would follow from Narayana. So this is saying that these are really hard numbers to compute, and so if you're like me and you like algebraic combinatorics kind of thing, this has a lot of implications for various numbers which come in algebraic combinatorics. And so, for example, Koski numbers, little Richardson numbers, and in fact are all strongly Sharpie complete. And something that complexity was completely up in the air. For Schubert coefficient, they are Sharpe complete, and that here a strong Sharpe completeness is extremely important, and also for Kronecker coefficients as well. So I'm not going to talk about complexity. This is just saying that the precise number is hard to obtain, so we're not going to talk about it much. Everyone okay with this?
Yes. Can I have a question?
Yeah, sure.
So what happens if we just count 0, 1 matrices?
That's those are very nice matrices, and it's all presumably very hard. We just can't prove it.
Okay.
But it should be the same story.
Mm-hmm. Thanks.
And in fact, lots of things I'm going to say applies to binary matrices. These are called binary matrices. And so lots of things I'm going to say about asymptotics and other things just transfer to them directly. But for simplicity, I'm never going to touch that.
Okay, thanks.
Everyone good? Okay. So now, why do people care? People care both from theoretical and applied reasons. And in fact, contingency table is one of those things which is somehow related to a million different parts of discrete mathematics. So one easiest part is they can be viewed as bipartite graph with fixed degrees. So if you have bipartite graph, then entry in the contingency table is the number of edges between i's vertex here and j's vertex there. And once you talk about these binary matrices, 0, 1 matrices, they correspond to usual graphs, and there is just a tremendous amount of literature on that, doing asymptotics and other things. I'm not going to review any of the literature at all. You can find some of that in Nick Wormad's ICM survey, and I'm just going to move on. And I'm going to move on in a rather intimidating manner by saying that there's just a lot of applications in statistics. Once you have dozens of books which have contingency tables in the titles, you know that these people are up to something. It's not it's not that they just wasting their time writing these books. So so I'm going to explain how it works in statistics in a minute. But before I do, let me make one important point. This is a point about connection between approximate counting and random sampling. So in fact, since we already know that you shouldn't be trying to compute these numbers exactly, approximate counting is the best you can do. One should understand that approximate counting is exactly the same as random sampling, simply because if you have a random contingency table probability that some entry, say x11 is greater than t, is exactly equal to the ratio of the number of contingency tables when you subtract from the first row and the first column this number t. And so if you have access to random contingency tables, that gives you information about the ratios on big and smaller numbers of contingency tables. And therefore, you can compute the number of contingency, approximate the number of contingency tables, sort of by recursion going down. And vice versa, if you have, that's an easier direction. If you do have some information about number of contingency table, you can conclude some information about probability. So my favorite example about statistics implications is this a kind of example that is more entertaining, that's truly practical. So here is a Queen Victoria who has been dead for a while, and apparently lots of her descendants have also been dead for a while. And one can ask the following question: is there a dependence between birthday and death day? And try to test it on these descendants of Queen Victoria, which are all recorded somewhere on Wikipedia and other places. And there are, and just like about contingency tables, there are actually books written about descendants of Queen Victoria. So somebody cares. And and the way it works is so Diaconis and Ephron in 85 came up with the way to test to test the independence, and the way it works is the following. You take a really large number of contingency tables, and then output a fraction of them, which has which has chi-square that's less than chi-square for the tables that you have. You see? So if the percentage is very low, that means there is some kind of dependence. This chi-square is not does not correspond to a random continuous tables with given margins, and if there is no dependence, it would have chi-square somewhere in the middle of the curve. Is everyone okay with the test?
All right, yeah. For someone statistically illiterate, what is chi here?
Chi-square, it's sum of the squares of the differences to what should be the mean. Let me not write that. It's
okay.
Maybe try to teach statistics once. You'll find out. That's what I did 20 years ago, and that's maybe the first time I'm using it. So, so it's pretty important to actually get this right. So one thing about this strange example is that by now we know everything about it, and in particular, so it's a pretty easy thing to calculate from the table that I showed in the previous slide, that chi-square is about 115, and so we're looking at random contingency tables with these sums and rows and columns. Do you understand what the table is? These are descendants. So this number 1 is the descendants who were born in December and died in March. So apparently there was only one of them, and some of these are zeros, some are 2s, and so forth. So the hypothesis that you want to do, and I promise there's not going to be much statistics at all. Me teaching it once doesn't really qualify me as an expert. So what people do is that they run Markov chains, and basically they plot the distribution of chi-square. And so here is what Diaconis here is Diaconis-Sturmfest plot from '98. And this is our plot with my former student Sam Dittmer that we did a couple of years ago. And apparently, if you the way they did it, the p-value, so percentage less than chi-square, is about 38%, and we get 0.1%. You see? And it's pretty important because now there are two morals of this. In the first case, you accept, and in the second case, you reject. So it is important to get the distribution right, because otherwise you might actually believe that there is no dependence between months of birth and months of death. Yeah, you'll be mistaken. But once you think about it, I don't know how many of you believe in astrology, but there shouldn't be any dependence, really, right? So, so the truth is, the model is the way we're modeling this thing is just not right. But somehow, people who have names shouldn't be modeled as part of the contingency, uniform contingency tables. But that's all I want to say about this example. Is statistics connection clear? Yeah. Remember, do this. Yeah, I wish more of you, more people were on video, because I can see some of you, just not that many. So if you are interested in participating and doing thumbs up, thumbs down, maybe you should try showing yourself on video. Okay, so now let me tell you a few results. The whole talk is going to be survey. I'm not going to prove much of anything at all. And one thing I want to tell you is that if you have very small sizes, if both sizes of contingency tables are small, Barvinek's algorithm just computes it exactly in polynomial time. That's we're going to come up. We're going to look into this a little later, actually, a lot later. But you can think of contingency tables as integer points in a large polytope, and in integer programming can be done in polynomial time and fixed dimension. So if you have the total sum very small, then you can also do it using dynamic programming, and that's more or less how you prove that when your total sums are all 3, for example, it has to be pericursive. In a different direction, Barvina and Foucault proved that if the ratio of the largest to the smallest is not too large, then and matches are close to squares, and you can do this in the quasi-polynomial time. So these are just some results that are known. The first portion is sort of non-probabilistic, and the second is probabilistic. So this is all using Markov chains. So what I'm saying is that if the row sums and column sums are very large, so roughly n to the 2.5 for a square matrix, then approximate counting can be done at polynomial time. Or in the opposite direction, if the row sums and column sums are very small or fairly small, then this can also be done in polynomial time. These are recent results. Or in a way similar to Barvina's case, if they have fixed ratios of rows and column sums, so for some fixed epsilon, the row set of n to the 1 minus epsilon, then you can also do it in polynomial time, which improves actually on Barvina et al. In 2 different ways. First, we don't have an upper bound here. And second, this is quasi-polynomial, and we have a polynomial time approximating. Everyone good with this? So that was a lot of results. So let me tell you a little bit how this works. And the way it works is the following. So here is the Aquinas-Gangolin Markov chain, sort of classical approach to the subject. What you do is you take a matrix, you choose 2 rows and 2 columns, and then flip a coin and try to add 1 or subtract 1 if you can. That's all there is. And turns out that this works relatively okay. This is what Diaconis, more or less what Diaconis and Sturmfes used when they constructed that graph. And but theoretical results, this is also what this is also what Dyer-Cannon Mount used more or less, and so in terms of polytope terminology, and in reality, it does seem to converge in polynomial time. So we have a completely different Markov chain with SAM. The way we did these things is by using Burnside processes by Jerome. I'm not going to explain much of that. But the way to think of that is this is a probabilistic version of Burnside lemma. And what I'm going to do is I'm going to explain a key lemma, sort of basic idea in the paper, which says the following. The contingency tables are in bijection to a set of orbits under the action of a giant product of symmetric groups. Now I'm going to illustrate it in a minute, but so the point is instead of thinking of contingency tables as some kind of multigraphs, which are objects by themselves, you should think of them as orbit representatives. That's it's a little hard to see how that works out. So, so before I move on, let me just mention that it is conjectured that basically both our Markov chain and the Aquinas-Gangolin Markov chain mix in polynomial time, and I believe that. Yeah, there is no way to prove that at the moment. So let me tell you why contingency tables are really orbits, and the way to think of about that is to look at this example. So this is an example of 5 contingency tables with row sums and column sums 3, 2, same vector. Now, if you have such contingency tables, so this is an example of such contingency tables, and I'm going to show how it's related to how it is related to being orbit representatives. So consider all 5 by 5 permutations where 5 is just basically 3 plus 2. So we're thinking of permutations as 0, 1 matrices. Yeah, permutation matrices. And now we're going to act on these permutation matrices by the product of SA1, SA2, etc. So in this case, S3 times S2 in rows by permuting the first 3 rows, the second 2 rows, and then by S3 times S2, the first 3 columns and the second 2 columns. And now you can see that if you start with this matrix, you can make basically, you can start doing the greedy algorithm, and you can put this in the kind of along diagonals, upper left corners, and in the remaining rows and columns that's not occupied yet, you can put more ones in the greedy way. And once you do that, then you can just basically look at what's the total sum of numbers in each square, and then output that in your contingency table. You see? So, so it takes a little bit of thinking, not too much, to realize that this is really a bijection. But once you do, you can just use Gerard's technology, which is fairly simple, and define a large Markov chain, which apparently works extremely well. So I'm not going to show you many pictures of that, but here is just one picture where we show that essentially our Markov chain for this particular birthday death day example, remember, descendants of Queen Victoria, that mixes in 5 steps. So here's a plot of chi-square, and you can, it's the same plot as you've seen before. And you can see that after 5 steps and after 100 steps, when you average over 10, I think this is 10,000 trials, you get the same distribution. And this is apples to apples comparison with Diaconis-Gangoli chain, which is in blue, and that approaches chi-square much slowly. And you can see that the mean becomes around 160, while if you look at if you look at this distribution, the mean is quite a bit off, which means that in practice, Diaconis and Stumpfes actually didn't do enough steps to get close to the mixing. They didn't know. Okay, everyone good with this? I'm gonna move on. So here is something kind of amazing. So suppose now you want to calculate exactly what's the number, or approximately what's the number of contingency tables. Apparently, there is a really simple formula which gives you a fairly good approximation. So this formula is by good, and it's just a product of binomial coefficients. Capital N is the sums of AIs equal to the sums of BJs. And what I'm just gonna tell you his reasoning, because the reasoning is fairly simple. So if you so how do you get this kind of formula? What you do is you think of S to be the set of all m by n matrices with total sum n. So the number is going to be this binomial coefficient. You with me?
What's the total sum? What does that mean?
Total, I mean, it's a rectangular matrix. You take sum of all numbers in the matrix.
Okay. Okay.
Is this clear?
Yeah.
Yeah. So it's really so the number is this binomial coefficient. That's pretty easy. And now what we do is we observe that the probability that such element from this large set has row sums A1, A2, etc. is given by the product of binomial coefficients. Here we just take into account the rows. And similarly, if you just take into account the columns, you get the product of kind of conjugate product of binomial coefficients. This one is with AIs and this one is with BJs. And now, if you all you need to do is to think of independence. What we need is both row sums and column sums to be exactly right. Now let's assume that this condition of having row sums A and column sums B are independent. If they were independent, then on one hand, this probability is equal to the ratio of number of contingency tables divided by the total number of such tables. And on the other hand, this would be a product of these two.
Mm-hmm.
And if you just do the algebra, you get this formula. Now, Good says that, after in a much later paper, he basically gives this argument and says, well, apparently I just confirmed the conjecture. This is a kind of almost a proof modular finer points of rigor. I mean, it's not really proof of anything, but that's what he says. Statisticians can get away with this kind of stuff. So one question one can ask is, does independence heuristic work at all? Independence heuristic is the formula that he's giving over here. And it works amazingly. It works amazingly, I think, for kind of unexpectedly. So for the birthday example, it works up to some percentage point. It's just 1, 2 to 6 versus 1, 2 to 1, 1. It's just amazing. And it's a little bit misleading. I think the first example is sort of random, if I may use this. So if you take this much larger example with a huge N in the 4x4 case that I showed you in the first slides that his was Delaire computed, then you get 10 to the 61, the same power, but slightly different constants of rho. That's also amazing. This is just like something that you cannot do using any technology. And it's also amazing because it's misleading, but you would have to try to understand why. I've tried a lot of other examples. This independence heuristic seemed to work. The part of the reason is it seemed to work is because there's only so far we can compute number of contingency tables precisely, and in those cases tend to be small, and independence heuristics tend to work fairly well for small examples. So so here are a couple of theorems both interrelated, and with basically Canfield and Mackay saying that independence heuristic really does work up to a constant. The constant is fairly nice; it's the square root of E, and so if your sizes become very big, then number of contingency tables really is the same as whatever is given by this product of binomial coefficients. And Greenhill and Mackay proved the same thing. Essentially, every time I'm stating the results, I'm stating them in a very special case. They have lots of conditions, but in essence, they prove that you get the same square root of E term for contingency tables, which are not with row sums and column sums fairly small.
So the lowercase n, right?
Where? No, this is an uppercase n. N is the total sum.
I see. Okay, the sum.
Are you good?
Sorry,
Okay.
did we say earlier that the row sums and column sums go down as you progress so that the A1, B1 condition really applies to all row and column sums? Is that a declaration we made?
I'm not following.
Oh, sorry. So it looks like the second theorem, this A1, B1 condition only applies to the first row and first column sum. Is that
Yeah,
true?
so I'm assuming here that just like in my long list of examples, row sums and column sums decrease in size.
Okay, yeah, thank you.
Yeah, so A1 and A2 are really maximal. A1 and B1 are maximal of them all, and essentially this is saying that yes, independence heuristics seem to work as far as we can tell. Now, the kind of a breakthrough was made by Sasha Barvinek, who decided that let's to look at a very different case. So consider, so suppose instead of, I'm just giving you a special case of what he proves. So suppose instead of everything being equal, we just have two types of marginals, Bn and Bn. So they're all linear, so that's is also fairly large margin, so they don't fit this framework. If B is strictly greater than 1, then he shows that logs roughly scale as n squared, and there is a limit in both cases for the independence heuristic. It's an exercise, but these limits are different. So in reality, independence heuristic strongly undercounts the number of contingency tables in this case. It's very far from being right. So part of the reason we don't see it in real examples is because we cannot do kind of like 100 by 100 with row sums and column sums equal to 500 or something. We just cannot do it in practice. We just cannot compute exact number.
Is it known how different the limits are, like how it depends on B or theta?
You know, in case of G, you can just compute the formula. In case of T, you can get an estimate. So essentially, I'll show you in a minute the idea what's behind Barvinek's approach. But formally speaking, he just proves he just proves the inequality. Okay. So before I explain a little bit more, let me tell you my latest result. This is so recent; it's just a few days old. This is with Han, who I can see in one of the squares in my Zoom. So what we proved is that if you have two types of margins, suppose number of BNs, the larger ones, is fairly small. It's not a constant proportion, but n to the delta. You see?
Yeah.
Where delta is somewhere between 0 and 1. So suppose you have very small number of large row and column sums, sort of like square root of n. Then apparently there is a phase transition, which is kind of hard to understand and even wrap your mind around it. So of course the limits that Barvinek considers are always the same, because essentially the number of contingency tables grows roughly like 2 to the 2n squared. But if you look at the difference between the logs, they scale as n to the 1 plus delta, but only for B large enough, and by large enough B greater than BC, which is about 2.4. And when it's small, the difference is just little o of n to the 1 plus delta. So there is some kind of second order phase transition. It's sort of easier to kind of visualize this function on this plot. So in some sense, so there are several kind of morals of this story, and one moral is one shouldn't really try to come up with a formula, because there is no way one can even see this phase transition at all happening. Mm-hmm. So all you can do is get kind of the leading term in the asymptotic, but lower terms in the asymptotics. So the e to the n to the power 1 plus delta. Let's say delta is 1/2, so n to the e to the n to the 3/2 term. You don't even see at all what it should be unless you kind of solve various equations and realize whether it's above or below the phase transition. So you need to know the phase transition. This is just the simplest case one can imagine when you have two types of sums.
I have a question.
Yeah.
How should we understand this? I mean, can we say this is something, I mean, are we seeing negative correlation here or positive correlation here as compared to Good's heuristic in the actual case?
Yes. So this that's correct. So it is saying that this is a there is a positive correlation, and it's actually kind of large.
Yes.
Because this ratio exactly, where was my fake proof? This is exactly this ratio.
I see.
If you convert it the right way. So in some sense, alternatively, the way I think about this is the following. You look at the block matrix, and this is saying that there's a significant correlation between entry numbers. So there's much more in the small upper left square that's concentrating when B is above the phase transition. So somewhat unexpectedly, this always happens. I'm getting very close to the end. So let me tell you a little bit about the combinatorial optimization approach. This is how Barvinek approached this problem. And the way it works is the following. So what he proved is the theorem that the number of contingency tables bounded by this function G and G times n to the minus. So remember, G grows like C to the n squared. So this grows like, this is much smaller, of course. So this is basically C to the n log n. And so from a theoretical point of view, one can think of that as a good approximation, whereas this G is a horrible function. So the way to think of that is you have some rational function, multivariate rational function here, which you optimize over 0-1 intervals. Now, the best way to understand that, this formula is hard to read. The best way to understand it is to understand how do you even come up with it. The way you come up with that is you look at the generating function for the number of contingency tables. That's a multivariate generating function or by the row sums and the column sums. That's this product over there. And now what you want to do is you want to find the best possible upper bound for this particular coefficient. So it's a large sum, and the way what you can do is you can try different values of xi's and yj's to optimize the ratio, because each coefficient is at most the ratio of the product and the whole function and that product. You see what I mean? And you have enough room for freedom, and apparently it works fairly well. Doesn't work extremely well, but works fairly well. You do, and so that's one thing. Another thing is using sort of combinatorial optimization, you can actually compute it in polynomial time. So this is computable. So that's Barvinek's approach to approximating a number of contingency tables. Is this clear? And essentially, he's using this idea of, so he sort of thinks of, he calls us typical matrices, which kind of like matrices which correspond to the, which correspond to these numbers G, and the one which optimize the energies. That's how he thinks about it. And so one should compare this theorem with our most recent result. This is a theorem I proved with Peter Brandon and Jonathan Lick just earlier this year, where we instead of this asymptotic term, which is nice, in reality Barvinek gets an explicit formula we get a much nicer product. So it's not even obvious, not immediately obvious that this is a better bound than that, but it is. We actually prove there is a better bound, and notice that we don't mess around with the upper bound. We only improve on the lower bound. Because at heart, we're using something not exactly what Barwinek does. We use a somewhat more recent technology with and the ideas due to Gurwitz and but the technology of denormalized Lorentzian polynomials to just improve on the lower bounds. And so rather than showing you lots of complicated formulas, let me just recall this birthday death example. In this case, we just have 592 descendants of Queen Victoria, and the number we already remember. It was computed this way. The heuristic works amazingly. So the old lower bound was about, due to Barwinek, was about 4.6 times 10 to the 8. We get 10 to the 12. Almost 10 to the 13 for the lower bound, and similarly for this large example computed by Jesus de Loera, the true number is 4.3 times 10 to the 61, and we get 5.8 times 10 to the 58. So which is what is about 800 times smaller. So that sounds like a lot, but in reality, there is not much of a competition. The lower bound by Barwinek he has different lower bounds. One of them is less than 1, so not very interesting. And another one is probably much better, but we can't compute it. Our computer's crashed. It just takes too long.
How well does the upper bound perform?
What?
How well does the upper bound perform?
Somehow the sound gets interrupted.
Oh.
In general, how bounds perform?
You gave the upper bound, like how far? Yeah, how far off is the upper bound?
Oh, they're both. Yeah, it sort of depends on the case. In our paper, we include a table of various values of the lower and upper bound, and the upper bound is okay-ish. It's not, but it's not fantastic, but it's okay. It's asymptotically, it's very good. In real life, it's quite a bit off.
So do you think
when you start doing this thing,
the upper bound or lower bound is closer to the truth? Is there a bias, or it depends on the case?
Depends on the case.
Okay, sometimes upper bound is better, sometimes lower bound is better.
And it also depends on which year you're talking about. In the future, probably one can improve the lower bound quite a bit more. I think improving upper bound is not going to work. So until recently, the upper bound was quite a bit better than the lower bound on a log scale. But with our lower bound, I think we're already beating sort of the low distance to the truth. And and there's some room for improvement, perhaps. So I want to mention one application, and the application is to volume of transportation polytopes, and the way to understand that is to think of contingency tables as integer points and some polytopes, where the definition in the definition, instead of being integer points, you just look at all real points. Which goes back to the first slide. And now Now, so these polytopes are very classical objects in combinatorial optimization, discrete geometry. One would want to calculate the volume, and the volume doesn't have a formula, obviously. If it did, it would give you a good approximation for the number of contingency tables. But from the lower bounds we have, you do get lower bounds for the volume. So, so we get lower bounds for the volume of general transportation polytopes just by using this formula relating the volume of a polytope and the asymptotics for the number of contingency tables when we expand it all by the same factor m in this case. And this is just a term, actually a square root of the number of spanning trees in a complete bipartite graph. Now, I should mention that this really is how confident Mackey obtains the asymptotic for the volume of the Birkhoff polytopes, where all sums and rows and columns are equal to 1. This, for decades, this was an open problem which they can resolve by in this direction by using the asymptotics of the number of contingency tables and applying it to geometry, the same direction as I'm doing. And let me just mention that essentially everything I'm saying also generalized to the case of kind of generalized contingency table when you fix some zeros in different locations in the matrix. When you go back to Barabinak's product, instead of taking all product over all INJ, you take only for those for which the zero is not fixed. And then you proceed roughly the same way. And so those are flow polytopes corresponding to this kind of bipartite network. But in reality, Baldoni, Diluera, and Michel Verne showed that this approach can be used to give lower bounds for the volumes of all flow polytopes. So in reality, our results actually give lower bounds for all the volumes. How good they are, we didn't check except for the Birkhoff polytopes when they are quite recent. And that's it. The left side is my picture of Santa Monica Beach in a normal time, and the right picture is from the news. That's what you see in Los Angeles these days.
Wow. All right.
Thank you all.
Thank you. Do you guys have any questions for the speaker?
So, I have a question. So for the volume of the Birkhoff polytope, the lower bound is better than the previous lower bounds?
No. Comfort Mackey computed the whole asymptotic.
Oh, so
it's a precise asymptotic. It's essentially because you know that the number of contingency tables in this case is the same as whatever is given by independence heuristic. You just compute what independent heuristic gives you.
Okay, and you can also give bounds for lattice points of flow polytopes from the last slide.
Yeah, that's what we get. I mean, it's you need to use both our complicated bounds, which become hard in the non-uniform case, and then you need to use this Baldoni et al. Bijection. But in principle, numerically, you can compute that. You can compute the lower bounds.
Could you I have a question? Could you make any comments on these multi-way contingency tables?
Yes, I can. So the question is about multi-way. Multi-way means high dimensions, 3 and more dimension. So there are two types of way to think about it. One way is to think of one-dimensional sums when you fix all coordinates but one. And the other way is when you have when you fix only one direction and all the others are allowed. So So the sums are over flats of codimension 1. And the first one is computationally intractable. This is an old result for counting this. The version is due to Delaware and on. So if you have one-dimensional sums, that's impossible to do anything. And if you have codimension 1, basically everything we do extends to that version. It's the same technology, same results. We didn't do. I mean, by that I don't mean that doesn't extend. The lower bound doesn't work. But whatever Barvinac writes works fairly well. And various Markov chain and other things translate to the codimension 1 case extremely well. So it sort of depends what you mean from a statistical point of view. Do you want to study much smaller set of contingency tables with more restrictions, or much larger set of contingency tables with fewer restrictions? And I don't know statistics well enough to give you a judgment which helps you to cure diseases and stuff. I just don't know.
Could I have a question? Could you go back to the transition slide where you have a couple of B and what's, yeah. So I remember that Barvinac had a conjecture that you have only one row and one column of, I don't know, 3n. And
that's correct. So we cannot do that. At some point, we're hoping that we could, but no, we can't. So this is the case when delta is equal to 0, basically.
Right.
So basically, we conjecture is that the same thing we're saying is going to work. We just can't prove it.
So if there would be a way to do it, then what would you like? What kind of method that you think?
We don't know.
Is there like you have to do like at the beginning you said that to study the distributions of one entry, then you need a more precise estimate on the volume, right, on the size.
That's correct.
And then you guys are not that you still some factor.
So we don't have a good answer for that. Han, do you want to answer?
Yeah. So everything we do is depends on the upper and lower bound that Barvinac gave. So the lower bound has big N to the minus some power. So if you take the log, that's the n log n. That's giving us n log n gap between the upper and lower bound. And so when delta is 0, your scaling 1 over n is overwhelmed by this error, the gap between the upper and lower bound. So delta should be positive in order to suppress the n log n error. So
Han is thinking of this term, C1 plus delta. If delta is 0, that's 1 over n. That's not enough for it to kill n log n.
So then you really need to understand the gap between the upper and lower bound. But when delta is positive, you can disregard the error term and then analyze what's given by the upper bound. So you basically need like a much better estimate, like at least better lower bound, much better lower bound.
Okay.
Yeah.
In that case, if you took B growing with N, would you see it behave like the supercritical phase?
It gets worse. It's just become, if B is much larger, let's say B grows like N, then basically everything is absorbed in that corner. Increasing B too much doesn't change random contingency tables.
I mean that by if you just have the 1 row 1 column version, do you see the correlation then? If it increases, yeah, you do.
That's a good point. That's a good point.
It's not a very natural case, but yes.
Okay.
So by the way, the slide you have here, does it include the case when B is at the BC?
We don't prove anything in that case.
Oh.
This is strictly great and strictly small.
At criticality, right?
All right. Other questions?
Okay, sounds like we're done.
Thank you so much. Great.
Of course, thank you. See you all.
Thank you.
All right, so I put it available on the seminar website, and then you can direct others to that. Okay, thank you, Igor.
Bye. I'm signing off.
Okay.